you're probably aware of the fact that you need to have a complete circuit for electricity to flow, and in this case, if I close this switch, we have 3 batteries in series making the light bulb nice and bright. One of the experiments that we look at this year is what kind of materials will conduct electricity. And it's a very simple experiment. What you will do is take the switch out of the circuit and replace it with 2 crocodile clips, like so. And when you connect the 2 crocodile clips together, the electricity can flow and the bulb comes on. We then have a set of materials to try. If I take copper as my first example, copper should be a good conductor. It's the one that we use in the electrical wiring. And there we are, bulb comes on. So we've got a conductor. If I take a non-metal at this point, polythene, which you're familiar with in polythene bags, so plastic, and plastics are generally insulators, not conductors, so the electricity doesn't flow and the bulb doesn't come on. And what you would do in this experiment is work your way through the different materials that we've got here, and there'll be a table of results. And if I just summarise them for you, if we take any of the metals, for example aluminium here, they will conduct the electricity, the bulb comes on. And any of the non-metals, for example wool, the electricity will not be able to flow through this. It's an insulator, bulb doesn't come on. But if you cast your eye down that list of results, or if you're doing the experiment, if you work your way through, you'll come across one exception to this rule, and that exception to the rule is carbon, or at least carbon when it's in the form of graphite, like this. Now carbon is a non-metal, but because of the way the atoms are aligned in graphite, the electricity can still flow, and so carbon is a non-metal, but it's a conductor. We come back to our original electrical circuit, and I'm going to take out most of the cells and just start with one. And as you're probably aware, if we have a complete circuit, the bulb comes on, but it's only got one cell, so it's not very bright. If I add another cell, I'm giving that bulb more energy. So we would expect the bulb to become brighter. However, you've got to be a bit careful when you do this, because you must make sure that the 2 cells are in series, not parallel, and that they are facing the same way. Otherwise the electricity that you're getting doesn't increase, and therefore the bulb wouldn't get any brighter. But with 2 in series like this, the bulb is definitely brighter. And if I add a third cell in series, again making sure they're the right way around, we get an even brighter bulb. So more electrical energy, because we've got more cells, batteries. That makes sense. In the same way, if I add an additional bulb in series, we're now sharing that electricity out, and so we get 2 reasonably bright bulbs, but certainly not as bright as the original one was. And if I go for a third bulb in series, and now they're very dim. In fact, the one in the middle looks like it's almost not on at all, but trust me, they're all on. Okay, so with series circuits, if you add more batteries, more cells, you have more energy, the bulbs will get brighter. If you add more bulbs, you're sharing the energy out, and therefore the bulbs will be dimmer. There's another problem with series circuits, which is if one of the bulbs should break. In this case I'm not going to break it, I'm just going to disconnect it. And although there's nothing wrong with these two bulbs now, no electricity will flow. So only when I reconnect this third one do we get a complete circuit. So we have an alternative way of arranging our electrical components, and that's what's called a parallel circuit. A parallel circuit has two advantages, though it looks a little bit more complicated. The main advantage, if you've got a parallel circuit, is that the number of bulbs doesn't decrease the brightness of the bulbs that you will see. So I've got here two batteries that I'm going to put in series, and we'll start them off with just the one bulb, and the bulb is quite bright, certainly as bright as the previous one was with the two cells. If I now add a second bulb in parallel, that is on top of the original, it looks something like this. And what's important to notice is that those two bulbs are as bright as the original one was. And if I add a third bulb in parallel, they are still as bright. And I could go on 4, 5, 10 bulbs. So that's really useful. And if you've got a set of lights or electrical sockets around your house, you certainly want them to be arranged in a parallel way. Otherwise, the more things you turn on, the less energy each one will have. So if you turn the television on and you were cooking dinner at the same time, you turn the TV on, the dinner would cook more slowly, for example. The other advantage with a parallel circuit is this. If one of your bulbs should break, the other two continue to work. And in the same way, if you've got a switch in a circuit, you can switch off one of the bulbs, or in your house, one of the appliances, the TV, the cooker, whatever, and the others can carry on. Or you can turn everything off when you're going out for the day, but leave the fridge freezer on, for example. And similarly, if you're cooking a meal, once it's cooked, you turn off the oven, you're not turning off the lights and the television and the fridge freezer and everything else. So parallel circuits, very useful in two ways.